I will talk about blockchain through the context of the Bitcoin blockchain. Now, there are many different implementations of the blockchain idea or reinterpretations of the Bitcoin blockchain. What we'll discuss today is one way of doing things. It's not the only one, but it's the first implementation of this kind that has some interesting properties like openness and decentralization. And that's why mostly I chose to talk about the Bitcoin blockchain. For me, the blockchain part ended up covering more areas than I expected. When I started reading and finding out about blockchains, I started with the technical part, which in itself has quite a lot of areas and information to cover. Then I got to the economics part, an area that is also quite complex and which for me was quite foreign. And then there is the part of interesting and strange communities and the whole history of those involved in various events around this blockchain phenomenon. Like, for example, in 2010, someone gave 10,000 Bitcoin in exchange for a pizza. Back then, 10,000 Bitcoin was about 40 American dollars, and now 10,000 Bitcoin has an exchange rate of over 100 million American dollars. Furthermore, I have come to see connections and parallels with real life when it comes to what it means to have a decentralized system, an open system in which anyone can participate and which can adapt to attacks. In this presentation, I will focus more on the first two, on the technical side and a little on the economic side. A starting point could be a discussion about money, but we will not go into too much detail about this in this presentation, such as why does money have value, or what exactly can be used as money, or what has been used as money in the past, such as stones, salt, or shells, gold, and why are not many of them used today as money? Or what are the properties that money could have, or the properties that it should have so that it can be used as money for a long time? Even if we do not discuss about this now, it is still an important discussion and it is important information. In 2008, Satoshi Nakamoto published a white paper, which is a document or report describing a way to have an electronic money system, peer-to-peer, meaning decentralized, without intermediaries, and yet, even if it is decentralized, the problem of double spending is solved. When it comes to digital information, it is usually not unique. It can be easily copied. It's like saying that we didn't steal a particular file, we made a copy of it. But when it comes to a good monetary system, we want to prevent this. And in January 2009, the actual implementation was launched, the code and the client that could be run. Satoshi Nakamoto can be a woman, or a man, or a group of people. No one knows, nor it is necessary to know. Satoshi was active for about 3 years on forums and email, and in 2011 disappeared completely, and the direction that Bitcoin was going to take remained in the hands of the community. But it is not the first attempt to create digital money. There have been various attempts before, but many have failed. Now, of course, there are successful implementations, such as PayPal, Alipay, M-Pesa. It is important to note here that some of them are payment processors with the transition of existing currencies into digital format, and some of them are attempts to create new currencies directly in digital format. What they all have in common is that they are centralized. They need a central authority, and Bitcoin is peer-to-peer. And it is not the first blockchain. Fun fact, the term blockchain is not even found in the white paper written by Satoshi. In 1995, some people who created a company named Surety wanted to ensure the integrity of electronic records. They used cryptographic hash functions, which we'll talk about soon, and once a week they publish in the New York Times the hash value of the information processed until then. So they marked the date using the New York Times, and the connection between the information is made with these hashes, since 1995 and still running. So, blockchain as a technology is not necessarily something new. The components that Satoshi used already existed in all these projects from the past. What is ingenious is the way Satoshi used them to solve the problems of centralization and double spending. One of the main components of a blockchain is to have a ledger, a register. A ledger, generally speaking, not just in the context of a blockchain, is used to record economic activity, such as transactions, and financial relationships, such as debt. And a ledger can keep transaction records or balance records. Bitcoin uses a way to store transactions. It has a transaction ledger. Ethereum, for example, has a type of balance ledger. It stores the balance. That's why in Bitcoin we have UTXOs, which means unspent transaction outputs, which we'll talk about later. So, one of the components of a blockchain is to have a ledger. Another main component is the use of cryptography. And cryptography can be used when we have communication in the presence of enemies, communication that must be protected, or when we need to check the integrity of calculations or messages, or to prove that we have access to a certain information but without disclosing that information. This makes cryptography fundamental in implementing a blockchain because it makes that blockchain easy to verify, preserves data integrity, and also by combining some cryptographic elements it solves the problem of double spending. Some of the technical elements used in Bitcoin are hash functions, Merkle trees, digital signatures, and public key cryptography is used, where we have private keys, public keys, and in addition in Bitcoin we have the concept of addresses. These are all existing technologies. Again, they already existed. Ingenious is the way Satoshi used them. A third main component is the idea of consensus, understanding, agreement about different rules within the network. It's the state we all agree with. It's a set of rules without rulers, without leaders, yes, because it's a peer-to-peer network. These are the rules followed by those who participate in this network. They are rules that determine the validity of transactions and of blocks of transactions. There are also some rules which could be considered as rules of the Bitcoin protocol. Two examples would be the fact that the maximum number of Bitcoin that will ever be created is a maximum of 21 million Bitcoin. This is the upper limit that will never be reached. There will be 20,999,999, something like that. This makes Bitcoin a limited resource. Another rule is that once in about 4 years, or more precisely once in 210,000 blocks of transactions created or mined, the reward, meaning those newly created Bitcoin, is halved. This term of mining is actually an analogy, because in order to extract, let's say, precious metals, the mining process is used, in which energy is required. Likewise, in creating new Bitcoin, energy is used. The idea is that initially, for the first 4 years, each new block of transactions also contained 50 Bitcoin. Blocks of transactions are created or mined approximately once every 10 minutes. So, every 10 minutes, 50 Bitcoin were created. After that, this number has been halved every 4 years. And this year, in May 2020, the most recent halving took place. And once in about 10 minutes, only 6.25 Bitcoin are created. And it will continue like this until approximately the year 2137, 2140, when all this Bitcoin of maximum 21 million will be created. So, we know exactly, it is written in code, which is the rate of issuance of new reserves of Bitcoin. And to give you an idea of where we are, so far over 18 million Bitcoin have been mined. Which means that from 2020 to 2137, there will be less than 3 million Bitcoin to be mined. The vast majority was already mined. It is an interesting, transparent economic system. We know exactly what is happening and how it's happening, so it's different from the one we are used to. Satoshi had quite good knowledge on the economic side, not only on the technical side. Now, what exactly is a blockchain and what is the Bitcoin network? The blockchain is the ledger part, and it's a list of blocks that contain information. Each block is added after the last one created, and so on, one after the other. The number of existing blocks can be called the blockchain height, the height of the blockchain. When that halving we were talking about took place this year in May of 2020, it happened at block number 6300,000, and since then more blocks have been added on top. So from 2009 until now, over 6300,000 blocks of transactions have been created or mined. That's to give you an idea of where we are. And this block with the number 6300,000 contains a little over 3000 transactions. Yeah, because a block of transactions can contain around 3,500 transactions. Each block contains information about the number of transactions in that block, the transactions themselves. It also contains a block header, which has various information, including a hash of the information from the previous block. The next block will contain the hash of the current block, and so on. In this way, a connection is made between these blocks, a chain of blocks, a blockchain. A block can have only one parent, but it can sometimes happen for a block to have more children, and each child has a reference to the same parent block through that previous block hash. This is called a fork, and it happens when different blocks are created, mined, at the same time by different miners. And what happens is that new blocks will be added on top of both variants, but in time this fork will be resolved, and usually the chain that will remain will be the chain that manages to become longer, the one that will have more blocks added, because it is considered to be the chain with the most energy used to have been created. These forks keep happening, but in the end they will be resolved and only one valid chain will remain. A copy of the blockchain can be held independently by different nodes in the Bitcoin network. Some nodes have a full copy of the blockchain, other nodes may have only a partial copy, that is, they hold only the information from the block headers, and some nodes may not even have a copy of the blockchain. Currently, the Bitcoin blockchain has a size of approximately 300 gigabytes. That's why not all participants can afford to keep a complete copy. The Bitcoin network is structured as a peer-to-peer network. It's an open network, meaning anyone can participate, and consists of nodes, computers, that run a software which is the implementation of the Bitcoin protocol. Software that is open source, meaning anyone can participate in verifying the source code, anyone can participate in improving the project. Yeah, and in this way the nodes communicate with each other, and a network is formed, because they are running implementations of the Bitcoin protocol that have the same rules, follow the same rules. And this is the consensus part. If certain nodes would start running another implementation, which has other consensus rules, then those nodes will no longer communicate with these nodes. The ones that will communicate with each other are the nodes that follow the same rules. It's something that has happened several times. An example would be Bitcoin Cash created from Bitcoin. The basic implementation of the protocol was copied, because the project is open source and anyone has access to it. Consensus changes were made. Some nodes chose to start running that implementation, and thus another network was created with other rules. This is called a hard fork. It created a hard fork, meaning a split in the network and in the blockchain. What is important to understand here is that the initial network is not affected. and each node chooses to follow the rules it wants to follow, and is going to be part of the network it wants to be part of. Now, the Bitcoin network has over 10,000 visible nodes, and most of them run the Bitcoin reference client, which is called Bitcoin Core and is the continuation of the project started by Satoshi, which is mostly written in C++. And a few of these nodes run other implementations of the protocol, written in various other languages, such as Node.js. Having the same rules, only written in different languages, means that the nodes will communicate with each other, and thus they all create the Bitcoin network. These nodes can be of different types. They can have different roles. They can be full nodes. These are the nodes that have a complete copy of the blockchain. Lightweight nodes are those nodes that have only a subset of the information from the blockchain. They only have the information from the block header. They could be mining nodes. These are the nodes that compete with each other to create new blocks of transactions. These mining nodes can be full nodes or lightweight nodes, and a node can just be a full or lightweight node without being a mining node. So if we want to participate by running our own node, we can do it without having to do mining. A component that all nodes have is routing, to be able to participate in the network, meaning that all nodes discover and maintain connections with other nodes. Also, all nodes check and validate transactions, and also propagate the transactions on the network. That's why many people or businesses run their own node that connects to the network, either full or lightweight, because that way they don't just have to trust other nodes, they run their own node. Another component they can have is a wallet, which is a way to store and manage private keys and addresses. So it is an open network in which anyone can participate. Anyone can maintain their own node that verifies and validates transactions. And it is a transparent blockchain, meaning that anyone can see the transactions that took place and the addresses involved in those transactions. And this is an overview of the blockchain part, which is the ledger, with its information and information about the transactions made, and an overview of the Bitcoin network, created by these nodes that reach a consensus. Let's now look at some elements that make the system work, such as cryptographic hash functions. And how they work is that if we have an input of any size, which we pass through a hash function, we will have as a result a hash of fixed size. They are one way, so from the hash we can't calculate back the original input. No matter how many times we pass the same input, the same value, through a hash function, the resulting hash will be the same every time. If we change only one bit in the input, then the resulting hash will be completely different. A good hash function manages to avoid hash collisions as much as possible. That is, when we have different inputs that result in the same hash. And because of this, the speed of a hashing function is important. If it is too fast, then it would be easier to artificially create different inputs that have the same resulting hash. So a somewhat good hashing function will not be extraordinarily fast. Bitcoin uses SHA-256, which returns as a hash a value of 256 bits, represented as a hexadecimal number with a length of 64 digits. No matter how little the input has changed, the resulting hash is completely different. Now let's see how this SHA-256 hash function is used in the context of Bitcoin, such as for the idea of proof of work used in mining. That is, creating new blocks of transactions that will be added to the blockchain. The first idea would be that each full node has independently a mempool. Just as we have nodes that each have a copy of the blockchain, each full node has a mempool, a memory pool, that has transactions that were sent on the network and which are not yet confirmed, meaning transactions that are waiting to be added to a block of transactions, block that will then be added to the blockchain. So these transactions are not yet confirmed because they have not been included yet in a block of transactions that will then be added to the blockchain, but they are valid transactions, because if they were not valid, they would not have even reached the mempool. Also, even though each full node has a mempool with transactions, these mempools are not identical between nodes. One node has certain transactions in the mempool, to another node maybe some transactions haven't propagated yet, so it has another list of pending transactions. Yes, we should get used to the idea that this is a distributed network. Using this mempool, each mining node separately creates its own version of a block of transactions that it wants to add to the blockchain. We will take this block as an example, and it will fill it with transactions taken from this mempool. How do mining nodes prioritize transactions? Simple. They choose those transactions that have a higher fee attached, because the mining node that will manage to mine this block will receive all the fees collected from these transactions, plus that block reward that we were talking about, those 6.25 Bitcoin, which were initially 50 and which will be halved about every 4 years. So if it can get the fees from these transactions, why not include them all from the mempool to get as many as possible? It can't, because a block has a maximum size, which is about 1 megabyte, and a block weight that could go to about 4 megabytes. There is a whole discussion about scaling the system, and that's why Bitcoin Cash was created. Some people wanted bigger blocks. The mining node will also need to create a block header that will contain some information. A version, which is a number that tracks software changes, that previous block hash, which is a reference to the previous block to which this mining node wants to add this block. It will need to create a Merkle root, and it does this by creating a Merkle tree of all transactions in this block, and it will result in a Merkle root, which is a value of 32 bytes. There will be a timestamp, which is in Unix epoch time format, and two more information that are important for the mining process. A difficulty target, which will end up being a hexadecimal number, and a nonce. With this information, it can start the mining process, which consists in the process of making hashes from this block header until the resulting hash will be smaller than the target. This is the key. This condition will have to come true. But if we have the same input, we'll always have the same output, so for the resulting hash to be different, something has to change in the input, meaning in this block header, namely that nonce, which means n once, that is a number used once. This nonce can start from 0, and what the mining node does is it will increment this nonce, 0, 1, 2, and so on, so that it changes something in the input, until it happens that the resulting hash will be a lower value than the target. The target looks something like this, and there is a formula in the code through which it is passed to be brought to look like a hexadecimal number of 64 characters, like the hash, so that they can be compared. This target is the same for all nodes. All nodes follow the same difficulty, and it will be recalculated once every 2016 mined blocks of transactions. Meaning about every 2 weeks, the difficulty will decrease or increase so that the average time for creating new blocks should be around 10 minutes per block of transactions. The process of calculating and recalculating the target looks something like this. Okay, this is the actual target for the block 6300,000, and after going through those calculations in the code, it ends up looking like this, so that it starts with a certain number of zeros. To find a hash lower in value than this target, it means that the hash will need to have a larger number of zeros in front. Yes, the lower the value of the target, meaning when it starts with a large amount of zeros, the more difficult it is to find a hash that starts with even more zeros. An example often given here would be if we have two dice, and after we roll the dice, let's say we want to get a value that is less than the maximum possible, which is 12. There is a high probability that we will get a value below 12. Only if we roll exactly 6, it would not be valid. As we decrease the number used as the upper limit, the probability that the dice result will fall below that number gets lower. If we want to have the resulting roll be, let's say, under 3, we should roll exactly 1. The same is true here. The lower the value of the target, meaning when it starts with more zeros, the more difficult it is to find a hash that starts with an even larger amount of zeros. And that's what the nodes that mine actually do. I've always heard that nodes that do mining solve various complex problems. What they're actually doing is running that SHA-256 hash one after the other, changing the nonce until they come across a hash that's smaller than the target. This is the mining process. But if we look at the maximum value that the nonce can have, that 4 billion and something, it is a rather small number compared to the hashing power of the devices used for mining. In the beginning, in 2009-2010, these mining nodes were actually simple computers, which used the CPU power. After that, it was discovered that the graphics cards are more efficient in making these hashes, and mining nodes started using the power of the GPU. And now, specially built devices are used to do just hashing. That's all they do. They don't use energy for anything else like a normal computer. That's why these devices can do over 10 terahashes per second. A terahash means a million hashes, meaning they can make more than 10 million hashes per second. So they can go through all those 4 billion attempts in less than a second. And if a hash smaller than the target has not been created in these 4 billion attempts, then it means that something else needs to be changed in the input, that is, in this block header, besides the nonce. One way would be for the mining node to modify a transaction called the coin-based transaction. This coin-based transaction is a transaction created by the mining node to receive the block reward if it manages to get this block through the mining process. So, in addition to the transactions that it already chose for this block, transactions that it cannot modify, the mining node can modify this coin-based transaction. Modifying this transaction also modifies that Merkle root, which was created by making a Merkle tree of the transactions. So the block header hash is completely modified, and thus the process of changing the nonce can be restarted from 0 up to its maximum value, and so on until a valid hash is found. For this block, the nonce found was 2 billion and something. But just by looking at the nonce, we can't tell how many hashing attempts there have actually been, but most likely there are more than 2 billion. And the hash of this block ended up being this one. It starts with one more zero than the target, because a mining node found a hash that starts with 19 zeros, compared to the target which has 18 zeros. Yes, success. The mining node has found a valid hash, and now it can transmit this block with this found hash to the nodes in the network to be validated. The nodes in the network receive this candidate block. They check the validity of all the information in this block, including checking the proof of work that this mining node has made. To find this hash, the mining node spent energy passing through many hashes. Yeah, electricity and money for that electricity, but to check its validity is very simple. Only one hash is needed. So for the other nodes, it's very simple to check if this candidate block is valid or not at the current difficulty. It is valid, so each individual node, the nodes in the network, will add it to their copy of the blockchain. The other mining nodes that worked on their candidate block number 6300,000 will stop mining that block and will start creating and mining for the block 6300,001, which will have in the previous block hash a reference to this block hash, meaning it will have as a parent this block 6300,000, which was just mined, validated by the network, and added to the blockchain. Yeah, we're all okay? We got here. Yeah, this is the mining process. Transactions are taken from the mempool until a block of transactions is filled. A hash of transactions is made to get a Merkle root, and then can start the process of making hashes from the information in the block header, modifying that nonce and that Coinbase transaction if necessary, until a hash is found that is smaller, meaning a hash that starts with a greater number of zeros than the current target. After a valid hash is found, the candidate block is sent to the network to be validated and added to the blockchain. This is the idea of proof of work. Energy spent to maintain network security. Other blockchains can run other systems, such as proof of stake, a system in which, instead of electricity, the funds that a node already has on that blockchain are used. They intentionally lock some of their funds for several blocks of transactions. They commit to validate the blocks correctly. If they don't validate them correctly, they will lose that money. If they do it correctly, after a few blocks of transactions, they will receive back their funds and fees from the transactions. It has pros and cons, as with any system. Now, let's take a look and see why this whole proof-of-work mining process is used. We saw that the blocks that make up the blockchain are actually linked together by that reference to the previous block hash. Block hash found by using energy. Yeah, mining nodes use energy to make all those hashes. Let's think about what it would be like for someone to attack the network and see what options they have and see how well an attacker could do. Let's say that someone is trying to change the history of the blockchain, trying to invalidate a transaction. Let's say it's an attacker, which can be a mining node or a group of mining nodes. They should go back to the block that contains the transaction they want to change and make the change they would like. When something changes in the transactions, there will be a ripple effect. The Merkle root will also change, which is resulted by creating a Merkle tree of the transactions. So the information in the block header changes, meaning it changes the block header hash, which must be smaller than the target to be a valid block. This means that the whole process of mining this block, that is, finding a valid block hash, must be repeated. And let's just say they could do this. But that's not all they would have to do, because if this block hash has changed, it means they would also need to modify the previous block hash of the child block, which is part of the block header, so the block header of this block is also changed. And so on. Yes? It's necessary to go through this whole process again, which consumes a lot of energy in order to revalidate this block as well. And the next one, and the next, until when? Well, let's not forget that this entity that is trying to change the history is working on its own version of the blockchain. And in the meantime, on the network, the process of validating and adding new blocks of transactions continues. It should go through all these blocks, plus the new ones added in the meantime, so that they somehow get, let's say, up to date. Now, the Bitcoin network consumes about 100-200 million kilowatts hour per day. To put this in perspective, a laptop can consume about 60 watts per hour, meaning in a day about 1.4 kilowatts hour. So they should consume at least this much energy. It's unlikely they would get here, to be able to revalidate these blocks and to catch up with what has happened in the meantime in the network. And if this attacker reaches in their own blockchain version the same blockchain height, the same number of blocks as the blockchain in the network, well, it will be the only one with this version. There are at least 10,000 nodes that have another version of the transactions. In vain, it comes with its own version. And here is the idea from the beginning about money. What has value? Why does it have value? It's like I would say that I have $1 million. And people could ask me, where do you have them? And I say that I have a piece of paper at home on which I wrote that I own $1 million. And I signed it. Well, that paper has no value to others. But if I had the papers printed for the American government, signed by American politicians, which add up to $1 million, then those would have value for others as well. Yes? So it changed its own version. Bravo! It put in the effort and consumed energy in vain. Then we remember that the valid blockchain that is the longest is considered the true one, because that's where the most energy was spent. This means that it should have enough processing power to also mine the next blocks, and to add them to its version of the blockchain, to make it be the longer one. And this would be a 51% attack. It should have more than 51% of the hashing power of the network. Yeah, so this attacker could have a better chance of mining the next blocks and not any other mining node that it competes with. But it competes with a fairly high hashing power of the mining nodes in the network. If we take the same point of reference, that block 6300,000, when the halving took place in May 2020, the combined hashing power of the mining nodes in the network was around 100 million terahashes per second. And we remember that a terahash means a million hashes. So currently the hashing power and the energy spent by mining nodes in the Bitcoin network is extremely high. It is not feasible to try to do such a thing. I would say it's even impossible. Because what can it actually achieve? To invalidate a transaction? That's about it when it comes to what it could do. It cannot do much. Like, for example, it cannot get for itself any amount of Bitcoin by rewriting some transaction and saying that another address should send to the attacker a certain amount. It would not be a valid transaction. That transaction should be signed by the entity who has access to those funds. So it's useless to rewrite any transaction like this, because it will not have a valid signature, and the transaction will be rejected by the nodes in the network. So the benefits would be anyway insignificant. This way, the blockchain is immutable. Once transactions end up on the blockchain, and more blocks have been added over, it becomes impossible to rewrite something from the past. If there is an entity that has a lot of hashing power, it has more to gain if it follows the rules of the network than if it tries to attack it, because it has a chance to mine the next blocks and thus to receive the fees from the transactions and that block reward through which new Bitcoin are created. Yes, so this is one function that this proof of work has. In this way, the blockchain becomes basically immutable. And now we can talk about the economic side as well. Related to this proof of work is the issuance of new Bitcoin, which takes place every time that proof of work is found, that block hash, and a new block is added to the blockchain, which happens approximately once every 10 minutes, amount that is halved every 4 years or so. Now, why is this process thought out so that new Bitcoin are mined every 10 minutes and not just have them be created all at once? It is somehow a process similar to the mining of precious metals. A way we can see this is if we look at the stock-to-flow model. That is, stock, which is the existing production, everything that has been produced so far, subtracting everything that has been consumed or destroyed, and flow, which is the, let's say, annual production, meaning what will be produced in 1 year. For example, the production of gold is about 1.5% per year from the total amount of gold which has already been produced. So pretty small. And it's like this, kind of constant, for many years, around only 1.5% per year. So it has a high stock to flow. Yes, because it is a large value divided by a pretty small value. When the demand for a certain good increases, this will cause their price to rise. Yes? So let's take an example for a few moments, based on an example given in the book The Bitcoin Standard. Let's say that overnight, for various reasons, the demand for copper will suddenly increase. So the price will increase and it will become more valuable. What happens is that the production, the mining of copper, becomes a more profitable activity, and because we are talking about copper, it is easy to increase copper production. Copper is easier to mine and is not as rare as gold. So, if production increases, the market will be flooded. Automatically, its price will decrease and a balance will be reached, and most likely it will be around the price it initially had. So, for an asset to not be affected by this, its value should increase when demand increases, and production should be somehow constrained so that it cannot be inflated, meaning if it has a high stock-to-flow ratio. And this is what happens with gold production and in the production of Bitcoin. That's why I said that Satoshi had quite good knowledge on the economic side as well. Every 4 years, the stock-to-flow ratio for Bitcoin increases. So this is another function of proof of work, and that's why there is that difficulty adjustment. New Bitcoin are created every time a new block of transactions is added to the blockchain, so there will be new Bitcoin created about every 10 minutes, and a halving of the reward around every 4 years, thus creating a transparent and predictable issuance rate. So we've had so far an overview of some important components that create the system, components with which anyone can interact directly, anyone can contribute to the software, anyone can participate in maintaining the network, but not everyone wants or can maintain a node with a copy of the blockchain that validates transactions or that even has a mining component. So we are approaching some concepts with which a simple user can interact, someone who just wants to receive, send, or hold funds. And this is what we'll talk about in the next presentation.